Thank you, everybody, for coming. I'm talking to you from my home in uh, the USA, in Texas, and I've been in this place for a very long time. As you know, we are all sharing a difficult time here, but we're making the best of it. And I want you to know that this is my very first talk of the year, and the very first time that I'm presenting in this manner. I'm going to try to do my best, and I hope you guys bear with me. And with that, let's get to the presentation because I've got a lot of material to talk about. And so let's get started. Uh, so here you are, the opening slide. This is C++ Russia 2020 Moscow, and this is me. Um, this is my book. And I'm here to tell you about this book that I've been working on for 20 years. This is me with my book. And I started this book in about 1998 after finishing my first book, Large Scale C++ Software Design, in 96. And this started out being a theory. And what happened is that I put it into practice over literally 20 years while I was writing this book. So this is a tour of chapter 0, which is the motivation for why this book is important. And the underlying thesis is hierarchical reuse. There are 3 more chapters in this volume. This volume is about process and architecture. There are 2 more volumes planned. In fact, I started volume 3 back in 1998, and I was working on it with then a fellow coworker who happens to be now the CTO of Bloomberg. And chapter 7, this volume goes up through only 1 through 3, is really quite a tight piece of work on verification and testing. The second part is design and implementation, but the final part is verification and testing. So with that said, that's the whole work. It's quite an ambitious part, but again, this talk is to motivate why I spent this much time working on this and living through it at Bloomberg, because this is what we do at Bloomberg. So let's get started. What's the goal? In any kind of software development effort, we have some levers, some slide switches that we can control. We can try to make it faster, we can try to make it cheaper, or we can try to make it better. And if we pick 2 of those, then the third one is pretty much determined. But what we'd like to do is find a process by which we can extend our abilities so that things can become faster, better, and cheaper at the same time. So starting in 2020, we create a process and we run it for 20 years, and then by 2040, we're better for having run that process. That's the thesis of this talk. And everything I'm going to tell you in this talk is geared toward making that happen. The rest of the book, the remaining 10 chapters, are details. We're not going to talk about the details here, but the whole motivation of this talk is the motivation to go and read the book and the second and subsequent third volumes when I finally get them put together. But hopefully this will motivate you to want to do that and to want to design in a way that yields more productivity over time through feedback. How do we do that? So for small projects, top-down design is the way to go. If you're designing something, you decompose it, and eventually you get to something that you can implement and you implement it. For large projects, that's grossly inefficient. Even within a single project, there's tremendous amount of redundancy. And so you wind up creating much more software than you would ever be able to maintain or reasonably produce. And so we need to find another way of doing business. So again, application software is typically top-down, collaborative, and malleable. Malleable meaning that it's easy to change. Library software is bottom-up, reusable, and most importantly, stable. If you have a complex application, it's often very hard to describe how you would spec out the whole application because it's often very unclear and business requirements are changing all the time. So there are, however, pockets within the application that are known to be useful, and we all can relate to standard components, for example. There are lots of standard components in any reasonable design because rewriting a hash map or a vector is just simply absurd. Now, if you go back 20 years ago, this was not as obvious, and people would rewrite things. This is common practice today. But to have even larger systems that are reusable was okay. Maybe we'll have a system that's reusable, but certainly not the parts. Now we find that often we'll build a system out of subparts, and those parts themselves are reusable. And we'll find perhaps even a large system that is decomposable into regular subparts and so on. This notion of hierarchical reuse is central to being efficient in the long term, but it doesn't happen automatically. So if we don't do things carefully, most of the code that we write will be in the application arena and we'll duplicate a lot of it. The goal, on the other hand, is to have most of the code that we write be library code. And by most of it, I mean, even though in size it's small, the amount that it gets used is large. So we don't have to maintain as much code, but we still get the value of very high quality software infrastructure. This is a good idea. Imagine we have a well-defined problem. If we don't do a good job at partitioning it, we wind up getting very jagged edges, and the metaphor here is a cracked plate. And if you imagine that we take a plate and crack it, the only place where those pieces could reasonably be used is in the original plate. There's no way we could ever use that piece reasonably in another location. An analogous story is, imagine your mother told you to go downstairs, make toast, and brush your teeth. You might build something like a toaster toothbrush to use. And of course, this is silly, and no one would ever do this. And yet, in software, people do build monolithic things that are unfocused and unusable in any other context. Sometimes we have more well factored pieces. They don't depend on each other, but they're clearly aware of their surroundings. Imagine we had a toaster with a hook and a toothbrush with a hole, and together they combine to satisfy some need. Again, this is silliness, but people do write software this way. This is less bad, but it's not ideal. So if what we're trying to do is write a program, then we can write it pretty much any way we want because we never plan to make any additional use of the pieces. If, however, we plan to have several versions of that program, then we need to make the pieces much more regular. Typically, that's the domain of collaborative software. But if our goal is to write software that's completely reusable across many versions of many applications, then we need to do better. Then we need fully reusable software. Reusable software is easy to describe. I often say that it has a small surface to volume area, meaning that it's easy to describe what it is and it does a lot for what you describe. So a particular colored rectangle, a blue square, a yellow semicircle, a green rectangle, something like that. Those are easy to describe. And they might do a little bit more than what you need, but you can compose them back into the circle. You can think of having a toaster that works on its own, a toothbrush that works on its own, and an adapter that connects the two. And all three of these pieces are reusable in and of themselves. So taking the reusable pieces, we can reconstruct what we needed. Putting them together, we can get back the original toaster toothbrush, but we also have the original pieces that we can compose to do other things. So now think about a monotonic block of software. This is a bad idea. No one would ever write a huge, large-scale block of software that's one piece. Who would want to compile that? Anyway, back in 1968, a fellow named Dijkstra suggested that the best way to design software is in a physical hierarchy where we have a first layer, or we have a first level, to be precise, of pieces, and those pieces are independent. Then we have a second level, and those second level pieces are designed to fit on top of the first level of pieces, and the third level on top of the second, and the fourth, and so on. And even though the interfaces to these pieces might be irregular, the idea is that the higher level pieces are designed with the lower level pieces in mind, put into place and tested in a way that is extremely effective. And he claimed, in fact, that this level of rigor was comparable to that of mathematical proof. Many would disagree. I, having lived through it for many years, don't disagree. I actually would trust a well tested piece of software more than I would trust a mathematical proof because mathematical proofs are proved by human beings and they're fallible. On the other hand, there's a fellow named Parnas in 1972 who talked about modular programming. And while his emphasis was not on the physical decomposition, it was much more on the logical decomposition where internal pieces could change and it didn't affect the greater good. Now, if you imagine that we combine both of these into one process and add to it a well documented set of interfaces, which we'll call contracts, we get the best of all worlds. Now imagine we have big pieces that we're going to decompose. This would be large, coarse layered structure. This, of course, is an improvement over a block, but it's certainly not enough. If we go to finer levels, this means that we have smaller steps between one level of abstraction and the next, but they're very wide, and so by using one piece, we obviously wind up depending on the whole block anyway. We could make silos where we have high vertical pieces where there is no gradations of abstraction going up, and each one is independent, but we're basically pulling together every level at the same time. So again, there's no reuse here. What we're looking for is, again, a combination of finely graduated and granular. And you can see that at every level of abstraction, we have something that we can use and reuse. And so this figure is probably one of the most important figures. It's been around for a very long time, and it's one I want you to appreciate, that at any level, not just at the standard component level, not just at the big chunk level, but at almost any level of abstraction, there's opportunities for hierarchical reuse. We're going to talk more about that as we go along. So if we have three pieces, the three pieces are probably built out of six pieces that are probably built out of so on and so forth, and you can see the hierarchy. On the right here, you see a toaster toothbrush is built out of a toaster, a toothbrush, and an adapter. The toaster has a case and a chassis. The toothbrush has handles and bristles. The adapter has an arm and a joint. You can see that this hierarchy goes down until the point where we have something that simply can't be subdivided. We're talking about things that are so low that normal people don't see them, like electrons and atoms and molecules, such things. Those are the things that people use over and over and over and over, but you don't know it because you don't really deal with those when you're writing applications. All right, so imagine now we wanted to create a toaster flashlight. How would we do that? Well, this is classical reuse because we'll need a flashlight. So here's the flashlight. It consists of a lens and a stock. The toaster flashlight reuses the flashlight, reuses the toaster, and reuses the adapter. The flashlight was of the toaster flashlight, but the flashlight is nonetheless reusable. For hierarchical reuse, consider that instead of using just the one level dependency, we're going to use a lower level dependency. So here we have a scrub brush, and the important thing to consider is that the scrub brush itself reuses the handle at a lower level. So the toaster scrub brush reuses the toaster, reuses the toaster, the adapter, and it creates a scrub brush that in turn reuses the handle. So on the right, we see the true benefit of hierarchical reuse as opposed to conventional reuse. Whenever we're creating a function that has a number of arguments or parameters, that takes a number of arguments and has a number of parameters, we could create it as one function. However, if something has 6 parameters, soon enough it'll have 7. If we design it properly so that we compose the 6 out of independent units, then when the time comes to extend it, we can have the original and the extended version, and all of the clients that depended on the original can continue to operate, and all of the new clients that need the extended functionality can continue to function. This kind of stability is essential when writing large systems. If You're developing some sort of client-server arrangement, and you have a protocol. Imagine you want to extend it. How do we upgrade it? You can't upgrade everybody in lockstep. You have to preserve the old protocol. You have to make sure that the servers get the new protocol, which is compatible with the old protocol, and then you have to upgrade the clients. What you can't do is change everybody in lockstep. So you need to support the notion of concurrent versions. One of the things hierarchical reuse does very well is support the notion of concurrent versions. Another thing we need to be able to do is support stability. So here we have an example where we have something and we want to write a function. We don't want to add a member function to a container. We want to write a function that works on the essential behavior of the container. And what makes containers extensible are iterators. And so instead of having to go in and insert a function into a container, we use its iterator and we extend the functionality without having to change it. This is known as the open close principle, and iterators can be used to write functions such as myAbsEqual, which I'm showing here. And again, I'm showing code. I don't expect you to read the code. It's more of a cartoon, but I just want you to see it there and know that it exists. Another example is maybe we want to print out things in a certain way. Well, by using an iterator, we can print something any which way we want, and we don't have to go in and write a custom print statement every time we need something new. With me just a second. Sorry about this. Oh. Okay, apologize. So here we have an account report writer that depends on a PostScript writer device, and we have a depends on relation between the two. And this is not a logical relation. This is a physical relationship. It means the account report writer somehow depends on the PostScript output device. And similarly, the PostScript output device somehow physically depends on the PostScript printer. The idea is we want to have our dependencies geared towards a fine-grained modular infrastructure that's reusable. So you see all these dependencies are trying to minimize the coupling, the physical coupling between the systems. That's what we're trying to show here. And all of our designs are about physical design. We'll talk more about that in a little while. This is well-factored software infrastructure. Now imagine that we want to write our same logical content for different output devices. Well, one way to do it would be to copy paste all of the code and make the appropriate changes. And I'm sure we realize that this is certainly not something we would ever want to do. Don't ever do that. A possible solution is to write something that is a manager that captures the idea of what it is to manage these three devices and presents a unified interface. Unfortunately, this is not something that is a good idea, because what happens is if anybody wants to depend on the output manager device, they automatically depend on all of the implementations. And so this is definitely not something that we want to do. All right. The better design, I apologize for this again. I should have thought of this. Let me see if I can get rid of this permanently. Sorry. I should have thought of this. Okay. That is gone. And this will be gone. As I said, I'm new at this, and I didn't realize that that would keep popping up. Okay, back to the real world. So anyway, here we have a situation where we have an abstract interface, and all of these things implement the abstract interface, and all of these things use the abstract interface, and all of these things depend on the common, well-factored software infrastructure. And this is an example of design that we might expect to see at Bloomberg or anywhere where we've tried to decouple the physical nature of the system so that each of the pieces can be used independently, and we pay in terms of link time and compile time and physical size for only those things that we need. Now, if you don't design this way, it won't happen. What'll wind up happening is if you need anything, you'll get everything. And that is not the way we want to operate. So These slides are taken directly from the book. This is an example of where we have a single client, and the client is in charge of making sure that the malleable or changeable software does whatever that software needs to do. And if that software needs to change, so be it. Um, the problem is if we have many clients, we can't have all of the clients asking for requests to change the reusable software because that is no longer reusable software. So unlike the malleable software that's managed by one business client, the reusable software is not managed by any client. It has uh, no one person or any person saying what it does. It does what it reasonably does, and you use it if it makes sense. And if it doesn't make sense, you don't change it. You you write something next to it that does what you need it to do. More about that in a minute. The unfortunate case would be if we had uh, multiple drivers trying to change the same malleable software. And the unexpected effect of that might be that we get something that makes sense to no one, like a flattened green toaster toothbrush with flag. Of course, this is a bad idea, and we need to guard against it. So now to physical design. What do I mean by physical design? Physical design is the arrangement of source code within files and files within libraries. As a verb, it's to partition source code among files and files among libraries. In other words, how do we arrange our logical content within the software modules that we're writing? And I don't mean C++20 modules, although I kind of do. And in fact, the C++20 module is modeled after what we have always called components. And it will turn out that modules done correctly are, in fact, components with a little bit more linguistic support. So what's a component? This is a schematic view of a component. It has a header file, and it has an implementation file. And in addition, associated with every component is a component level test driver file. Now, historically, we've always used separate files. It's not essential that it be a separate file, but it has very nice properties because you know that everything that you need to compile, link, and test this component and all its dependencies fits nicely in one single physical entity. And the good news about that is there's no equivocation. You absolutely know you have what you have. And this also serves as a measure of complexity. If it can't be tested from a single file, it might be too complex and deserves breaking down. So this is an example of component. I don't expect you to read the code. This is just a tour. At the top, we have the name of the component. We have the include guards. We have a class iterator that will be used in the container that we're about to talk about. This is a stack class. It's just an integer stack class. Here are the free operators for the supporting iterator. This is the actual stack class itself. Here's the private data. Here is a public type. Here are the creators, which are the constructors and destructor for the class. Here are the manipulators. These are the non-const member functions. The accessors are the const member functions. And then we have the free operators for the principal class. And this is what a typical small component looks like. Again, I'm showing it to you here just for your information. We're not talking about the details. The entire book is about how to design and write, implement, and test components. So, and by book, I mean the all 11 chapters. So this is a long story, but I wanted to show you anyway. And of course, here's how we print it. This is the last part. So looking at it schematically here, we have a stack that uses a stack inter in its interface. What does it mean to use something in the interface? A function uses a type in its interface if it names that type as part of its parameter list or its return type. A type uses, a function uses a type in its implementation if it uses that type somehow, but not in its interface. So we have the white bubble here means that it's used in the interface, and that means that you're using that type programmatically, and people know that you are. And here you're using it in the implementation, and while it's not used programmatically, it still generates the same physical dependency. Okay, a type uses another type in its interface if a member function of that type uses the type in the interface. So with all that said, we can have very complex logical interactions among logical elements within a component, but the physical view is the same always. We have a physical interface and we have a physical implementation. So if you imagine a simple component that has a class point, there's just a class. That's it. Imagine a set and its iterator. It's a little more complex, and yet the physical interface is the same. Now imagine a graph. A graph might have many interacting pieces that are essentially essential to that component. Why we put more than one logical entity in a component has to do with some specific reason, and those reasons are discussed in detail in chapter 3 of the book. The primary reason to do so is friendship. There are other reasons, but primarily the reason to do it is friendship. If it isn't a friend, it probably shouldn't be there. And then the fourth one is even more complex. Again, all of these pieces are forming a facade. All of them have private access. And clearly, we can't implement all of this in one component. We'd have to implement this as a hierarchy of components where this component is simply the dashboard that controls the functionality. So what do I mean by that? All these components have roughly the same within a reasonable factor, the same amount of code, of source code in them, but they do very much different things. So let's take a look at a physical hierarchy of software. And by hierarchy, again, I mean physical dependencies, not inheritance hierarchy. There's no inheritance going on here necessarily. So at the lowest level, we have a point. That's a leaf component. It doesn't depend on anything else particularly, although that's not really true. We can think of it that way. In fact, it probably would depend on other lower level parts that have been factored out. But for our purposes, let's say that a point is a leaf component. Then we imagine something like a map, and the map might depend on other lower level things that are used to build containers and such. And so the next thing might be at the top. It's a matching engine. It's very complex. It's not that much bigger. It depends on a lot of other things. But as you can see, um, it's at the top of the physical hierarchy. It can delegate, much like the CEO of a company is not a bigger human being than any of the other human beings, the line managers or the line workers that work for the CEO. But the CEO can delegate to a lot of other people, and therefore the scope of the CEO is much larger. I'm going to take a quick pause for questions now, and then I'm going to go on to talk about an analogy. But I do want to stop here and see if anybody has any questions.
Yeah, not that many questions, but since you were mentioning components, that looks conceptually very similar to modelers, actually. So I would actually like to ask you some kind of a very practical question here. So in terms of the recent language standards changes and the recent language evolution, do you see some particular things in the language which actually help building these large-scale software systems? Maybe some like models or concepts or whatever you think is valuable for the large-scale systems particularly.
Okay, so to answer that question, interestingly enough, we chose to write this book, at least volume 1, in terms of the C++ 98 subset of C++. And yet, we do all of the modern, we're very much on top of the modern design practices. We're very much involved with modules, concepts, very involved with contracts, and in fact, memory allocation as a language feature is something that we're very much working on. However, the only thing that really remotely affects the physical structure of software is modules, and modules really are a better support for .h.cpp pairs. What they do is they enforce two very critical rules. One of them is they don't allow cyclic physical dependencies. The second is they don't allow what we call long distance friendship. They don't allow friends to go outside of the module. These are the two most important design rules in the book, and modules enforce them. So to answer your question, with the exception of modules, there's really nothing in modern C++ that makes good design better. That's good physical design, because we're talking about something that's almost language agnostic. However, modules do provide direct support for encapsulation that does not exist with that h.cpp pairs. So to answer your question, modules, yes. And in fact, when I gave the talk on modules, I used slides that were 10 years old, and I just simply called the components modules. And at the end, I told people this slide deck is 10 years old. So I just want you to know that modules and components are the same thing architecturally. It's just that modules are better linguistically at doing encapsulation. They do not help with what we'll call insulation. They don't help with compile time coupling. They do help with avoiding logical coupling.
Okay, thank you. So does that mean you're satisfied with how the current models in C++20 look like, or maybe you're wishing them to be kind of different?
Okay, so the biggest challenge for modules, the library doesn't have a modular library rendering yet. Modules were put out so that they could get some experience. We at Bloomberg are actively working on modules and prototyping them and trying to refine them and make them even more valuable than they are right now. The most important part of modules is that they can be adopted incrementally and independently of other software that isn't going to be modularized. And so, yes, we want to make them better, and it will take a fair amount of time before they can be introduced into large code bases, I suspect.
Mm-hmm. Okay, thank you. Maybe slightly different here, but still connected. So for like large-scale systems and library-based designs, like seems like managing dependencies becomes critical. But however, in its C++ years, still the C++ language still lack a default tool for that. Like we have some tools like Connet, VC package, and others, but there is no standard. So do you consider this to be a problem, or do you solve it in some other way in Bloomberg, or like other thoughts on that topic?
Okay, well, there is no tool that helps you design software properly. You have to know how to design software properly. Tools can help, but the idea is you have to have a design that's acyclic in its physical dependencies. And so this is central to the first volume of the book. The chapter 3 talks about levelization techniques, and a great amount of the book is devoted to avoiding cyclic physical dependencies. So my suggestion for a standard would be to read the book and follow its guidance. And then we are working on a tool at Bloomberg to help visualize designs that are so constructed. And this visualization tool may be something that we can share with the world at some point. But this is not. This is in its nascency. It's not something that we're suggesting at this time. But absolutely, the best thing to do is to understand how to avoid cyclic dependencies, and the best way to do that is, I would say, to understand levelization techniques, and there's a book on that.
Okay, thank you, John. I think we can continue, so maybe let's go on.
All right, I will proceed. So, top-down software design is hard. It's a recursive partitioning problem. We're attempting to optimize a complex cost function. And by complex, I don't mean complex numbers, of course. I mean it is a very involved subjective cost function. But ultimately, we'd like to come up with a software design where the lower level pieces are inherently reusable. That would be amazing. We'd like to just somehow intuit when we look at something that if we design it this way and partition it this way, that every single subpartition is useful. Wow. How do you do that? You know, it's really hard. It's a combination of top-down design, bottom-up design, and a lifetime of experience of many people. And what happens is that if you're trying to do this and you try to do it over your entire lifetime and you're lucky and skilled, it might happen. If you don't try to do it, it will not happen. And so I just want to explain that this is a very hard problem, but it also is worth solving because it produces tremendously good results. So, with that said, I'm going to give you an analogy. This is a very complex analogy, and I'm going to run through it fairly quickly. If I lose people, I apologize. The gist of the thing is to say that the act of partitioning software and software design is really hard. Let's pick something that's more tractable and try to solve it. And notice how in solving it, we are actually applying a technique called dynamic programming to design. So here's the analogy. Suppose that we want to write a program to format function documentation that avoids leaving lots of space at the end of a line due to a very long word like my very long type. If you notice this, we have these ragged pieces here. That's a ragged piece. That's a ragged piece. It doesn't look very good. We'd like to do better. Notice on the right, it's nice and smooth. How do we do this? So let's think for a second. If you had to solve this problem optimally, what would you do? Now, the algorithm on the left simply puts as many words in place as it can, and then when it runs out of room, it goes to the next and the next and the next. This algorithm runs in linear time because the cost function is cheap, right? It's not a global cost function. It just does what it does at every point. But suppose we had the following global cost function. We say that not the sum of the spaces at the ends of the line, because if you look over here, this is very, very bad. We want to assign a disproportionately large cost to that. We want to assign a medium cost to that. We want to assign a very, very low cost to the other lines so that the sum of a bunch of medium spaces with some function of them is less than a big long one and a short one. And the way we do that is we simply cube it or square it or take it to the fourth power. But if we do that and we sum them, if we say that we want to minimize the sum of the cubes of the trailing spaces at the ends of the line, that would give us the thing on the right. That in fact does give us the thing on the right. So let's look at that. We have a sequence of words on lines 1 to L. So there are words. We have a total cost function, and we're saying on each line from line I equals 0 to line m minus 2, m is the number of lines, we're going to calculate the sum of the cubes, and we're just going to say if we partition the words the best we can so as to minimize that number. Now, if you look at that and you try to do it by hand, you'll realize quickly that that's not a super easy thing to do. It's expensive. Let's look at what we mean here. Here we've done the greedy algorithm where W2 is at the top. We didn't try to fit it in where there was space. On the right, we decided, wait, I think we can do better if we wait with W2. So on this line, the two partitions are different. You notice that 1 squared plus 9 squared and 5 squared plus, this is 1 squared plus 9 squared, and this is 5 squared plus 5 squared. The one on the right is smaller than the one on the left. And because of the way we set up the cost function, we'll get a smaller result. This is a better partition numerically. So we now have a formula for what we want to do. And now I want to solve this problem. How do I solve this problem? So I'm going to propose a recursive solution, a recursive top-down solution that says what I'm going to do is, well, let me before I describe the solution, let me describe the code. So what we're going to do is we're going to, instead of creating what most people do is they create a main program. We're going to start with creating a utility function. And most application developers start with a main, but most library developers start with a util. And I'm a library developer most of the time. And so I start with a util. And so what I'm going to do is I'm going to create a namespace for a function. And this is my namespace. And this is my function, calculate optimal partition. And this, I'm just going to put this up so that up so you can read it while I explain that the purpose of this function is given a vector of word lengths and given a line length and given a cost function, this is going to return a partition as a vector of indices. So this function is the guts of the problem. And once you have this function, all you have to do is write main and implement it, and you're done. So again, I want you to think about how library centric I am. I go right to the library and find the reusable function and try to make it as reusable as possible. So here's my application. I don't really care. Applications are not important. They're a dime a dozen. I could have 10 applications using the same thing. This particular application specifies a cost function. It has some helper function to do some analysis. It has a main program that does some stuff. It invokes the library function here after it collects the information. It prints the results. That's all a main is, and we don't really care. We're done. Now we need to implement it. And so what we're going to do is this. The design for implementing the function is I'm going to see if whatever is given me fits on a line. If the answer is yes, I'm done. If it doesn't fit on a line, then I'm going to take the problem of however many words I have, and I'm going to partition it into two problems as many ways as I can. And given that I have n words, there are n minus 1 ways to partition that problem. You can just sort of see it. And so what I'll do is I'll create each of the n minus 1 partitions, call this function recursively, get the best sum with the lowest cost, and then recombine them and return it. So then I'll load the result and return the combined cost. At the highest level, it's a recursive solution to a problem. It's the same kind of thing we do when we do divide and conquer. It's the same thing we do with top-down design. We take a problem, we decompose it into subproblems. We take those subproblems, we decompose them into subproblems. And mentally, we try to figure out what the best decomposition is at every point in time. The software design problem is unbelievably harder than this problem, and yet they share many common properties. So here I'm going to show you the code in C++, but I don't want you to read it. I just showed you the algorithm. This is the local context that we're going to pass from recursive calls. This is the actual signature of the function that we're going to implement. This is the recursive call. This is more code. And this is the top level utility function implementation that sets up and invokes that recursive function. And again, I'm just putting it out there for you guys to look later. It's in the book, but that's not the point. So the problem is that this works. It's very easy to write. It gives the right answer, and it has exponential effort to do it, which is really unfortunate. Now, what can we do to make it better? So think about this. There are not an exponential number of unique problems to solve. Do you see why? We're doing a recursive decomposition, but over and over and over, we will run into the same subproblem. This is the same as what happens in software development. Over and over and over, you run into the same subproblem, and you have to solve it again. Only in software, you have to maintain it forever. We must avoid this. Think about this. Given n words, every unique subproblem can be expressed as a pair of indices ij, 0 less than I less than j less than n. Think about that. Every subproblem can be expressed as an ij pair where both I and j are less than n. That means the number of unique problems is order n squared, not exponential. If there are only an n squared number of problems, why is it taking me exponential time to solve it? Why does it take so long to write large systems? What we're going to do is we're going to employ dynamic programming. We're going to do what any programmer should do. If the solution to this problem already exists, use it. Otherwise, do what you did before. And then put that solution back for others to use. Nothing else changes. This is dynamic programming. The beautiful thing about dynamic programming is you can add it to a recursive program and it just works. So I'm going to show you what this looks like in code only in the sense that I added it to the code. And see where it says new? I just added it to the code. The beautiful thing now is that whenever I start out, if you think about when you start out doing software development, the first program you write, you have to do all the work. You have to set up your environment. You have to write all the common subroutines and blah, blah, blah. Once you get that done, the next program is easier. The next program is easier. And eventually, by the fifth program, you're really cruising. Anybody who's moved to a new job and started there realizes that they're not very efficient when they first move. Thank goodness for laptops and portable environments. But back 20, 30 years ago, when you moved, you started over and it wasn't fun. So I'm saying that this same thing happens in software development, and this certainly does happen in text partitioning. So if you look at the advantage that you get for problem sizes of 1, 5, 10, 15, and 20, look at the amount of reuse you get very quickly. Now, this is an extreme example, but this particular example is very near and dear to my heart. Dynamic programming has actually helped me to get patents. It's part of the design of many things that we do mentally and in practice, and it actually applies to software design. Dynamic programming and software design is really the thesis, again, of this entire series of books, because what it yields you is the hierarchical reuse of low-level sub-solutions. So again, this is a big deal. Let's belabor this a little bit more. So what we're doing here basically is whenever we get a solution, we're creating a vector, that partition. And we're building up a map, and it says between this range and this range, we get this partition. But this is copy paste. You'll notice some partitions for the whole range are much larger than others. We don't have to copy the partition from one to the other because at the lowest level, the partition exists. Instead of copy pasting it, we could reference it. So imagine at each point, we have a node that says, here's the subrange, here's the combined cost, here's the left node pointer, the right node, the left node pointer, the partition index, and the right node pointer. And this node carries enough information that when other nodes refer to it, you can reconstruct the entire piece. Notice the hierarchical reuse going on here. Okay. In this case, it's not cut and paste, it's by reference. The other thing is that each component, notice I said component, is fixed size. So no matter how big the range is, it's built out of fixed size components. What about this map? Now, when you're developing software and you have a huge infrastructure library, it's very important to have a way to get at things quickly. So the faster you get to the solution, the better. If you have a whole bunch of solutions and you don't have a way to find them, then that's going to be the bottleneck in your design process. So let's see what we can do to make this better. We could use a balanced tree, which is a stood map. We could use a hash table because we don't really care about the ordering. But because it's a triangular array, we can know in advance exactly how much space to allocate and get to it in constant time and quickly. And so having a curated solution set where you can put your hands on each curated component solution quickly is the genius that makes this analogy the best it can be. So let's recap. The original solution was untenable. We used dynamic programming to make it at least feasible, but it wasn't efficient due to cut and paste reuse. Then we broke things down into components and referred to them by reference, and we saved an order of magnitude in space. And notice how much better things got. Then we said, you know what, let's get rid of all of that overhead and just put things in a nice contiguous array where we'll get all our caching effects and everything wonderful. And now we can handle much larger problems very quickly. Notice we can handle 1,000 words, get the optimal result, and we can still do it in 36 seconds. But that's simply because the machine I was working on at the time, and when I did this experiment about 15 years ago, it turned out that that machine didn't have enough memory to handle it. My machine today would crush this. Anyway, just to drive this analogy home, and I'm going a little bit over time, but we'll take some questions in a second. Subjective cost function in software development, objective cost function here. Application program, suite of programs, the entire text. Factor design, partition. Logical content, words. Leaf component, align. Back up. Leaf component, align. Component, a solution. Hierarchically reusable library, a solution cache. Enterprise-wide, globally accessible. Source code copy and paste, independent solution copies. Software packaging strategy, curated suite of components. Solution cache organization again. Uniform component size, uniform solution node size. Reusable software is stable. Sub-solutions are never modified. Component dependency, reference to sub-solutions. Finding relevant components, finding solutions quickly. So that's the analogy. Again, what I want to make clear is that this is an example of a problem that appears to be really hard. And if you keep reinventing the wheel, it's exponentially hard. It's exponentially hard in terms of the time to recalculate it each time. In software, it becomes hard to maintain all of that duplicative software. So with that said, I'm going to pause for some more questions.
Thank you for the great analogy, John. Actually, not maybe a question, but just a comment which you would like maybe to address. Like, personally, to me, the complexity sometimes looks scary in such systems and when you try to reuse that many components. So is there any structural approach to storing all these components which you're trying to reuse, building the kind of a library or something? Just because when there are so many things and so many blocks you could reuse, you might be maybe losing yourself in the amount of them and forgetting that there are some blocks doing the same things.
Okay, so the answer to that question will be slightly addressed in the next part, which is short. But
Okay.
the answer to the question is you can't make this happen by magic. And the way you do it is when you start a project or when you start a group or when you start a company or an enterprise or anything, any part, subpart, sub-subpart, or whatever, you have a plan. So if you were going to move into your office, would you just put all your books in there or would you build a bookcase? So if you plan to put in file cabinets and bookcases and whatever, what that means in software is you have a software infrastructure that is itself hierarchical. And so, as we'll see, by design, when I go into a group and advise them, I say, okay, let's talk about your major functional entities. What are and what we call those is package groups. Package groups are collections of packages, and packages are collections of components. They're named entities. Now, they have very short names so that they can be identified in the code. And this is the topic of Volume 1, and you can read all about how this organization happens. As I said, I'm motivating you here to buy this book. If you buy this book, it will give the answers to every single question you could possibly imagine about large-scale C++ software design. It is all there. It is all there in terms of organization, in terms of naming, in terms of dependency. It's all there. But the basic answer to your question is you'll need 3 levels of physical aggregation: package groups, packages, and components. We've mostly been talking about components. We will need to organize them into packages. They will in turn need to be organized into package groups, and package groups will have to have an acyclic physical dependency graph throughout your organization. And that's about it.
Okay. Then maybe next question before we continue. Like when you write a piece of code, you might spend some time and, for example, generalize it, and put it to some component to reuse in the future. But this will take time. This will take like some effort from you, some resources. So should we actually spend these resources every time we implement some functionality, or maybe we should just find some balance between like copy pasting and not spending the resources on generalizing, or generalize every time you implement some new solution or some new piece?
This is an
So do you know,
excellent
like,
question.
is there any
I,
balance somewhere?
I understand what your question is. Of course, the answer is there's always balance, but it's not a balance between cut and paste. Here's the thing: the way you generalize is not by making something more complex, it's by making it simpler. I know that's counterintuitive, but in the next section, I'll bring this up specifically. What you need to do, most people think that in order to generalize, you need to create 120% of what you need today. That's not true. To generalize, you need 80% of it, and you write the 20% to customize the 80% to what you need. Then the next person comes along and they customize the thing to what they need, and so on. So you write, as we did with the utility class here, we did most of the work for people and we wrote a utility class, a utility struct function. And then the application developer comes along and customizes what they need and reuse that function. That function will never change. And yet 10 applications can come along and use it. So if you're writing this application, your goal is to find the 80% that's reusable and write that, and then write the 20% that's malleable and write that, and leave behind the 80% for others to use. Does that answer the question?
I think yes, and maybe we can then proceed to the next part with that.
All right, it was a really important question. Thank you for asking it. All right. So in business, time is money. And if company a company at T1 gets something to market, they get all the money. And by the time company 2 gets to it at time 2, there's less available profit. And over time, the marginal profit reduces to a commodity and there's not much value. So sometimes it's worth doing something quickly just to get it to market and then doing it over. There's a phrase, there's never enough time to do it right, but there's always enough time to do it over. Well, another approach is we think about the Mythical Man Month. If we just throw more people at it, maybe we'll get it done faster. Of course, this doesn't work, it doesn't scale, and it's not how things, it's not a sane way to run a business. It turns out that staffing profiles are typically a power curve that looks something like this, where they grow over time to some optimal value, and then as the product nears completion, it decays through testing until some reasonable bug rate occurs, at which point the software is shipped. There's still bugs, there's still people working on it, but it looks something like this. What are we going to do to improve time to market in the future? What can we do today to improve time to market in the future? And the answer to that question is to provide software capital. Software capital was originally sold as being something to reduce maintenance costs. By having a highly reusable software infrastructure, we don't have people reinventing things and therefore spending time and therefore having to maintain more and more software. That's its secondary purpose. But its charter is to reduce time to market for future applications and products. What does software capital need to be? It needs to be easy to understand. It needs to be easy to use. They're not the same. Easy to understand means it's approachable. Easy to use means once you understand it, it's efficient to use. Not in the sense of performance, which is also important, but in the sense of developer productivity. If it isn't high performant, people will write it themselves. In fact, we want our software to be so high performant that no one in any reasonable amount of time could come close to having it be as performant. Which a little bit goes to the question is how much effort should you put into software capital? The answer is a lot. It's an investment. It also needs to be portable. We need to make sure we stay within the language. So if we go outside the language and what we write is not portable and a new architecture comes along, we may miss a business opportunity. And finally, reliable. And I mean no core dumps, no memory leaks, no incorrect results, no bugs, and no, we're not kidding. And that means thoroughly tested. This software has to be as good as the compiler itself. And it may sound like that's just talk, but no. In fact, with the kind of test methodology described in volume 3 of this book, such is absolutely possible. When you combine the design, the highly factored design, the careful implementation, and the thorough testing, this volume set teaches you how to build software capital properly. Of course, it has to have all the properties of physical design, acyclic dependencies, no long distance friendships, et cetera, all discussed in volume 1. Okay, so now imagine we have this warehouse of products. They're all on the shelves, they're all ready to go. You'll notice that each row, if you will pretend that's a package group. In each row is a package, you notice that little shelf, and each one of those components sitting in the group there is sitting on the shelf. And what we do is we say, gee, let's say we need a D or an F or a W or an I. Well, all of these things in row 4 are built in terms of things in rows 3, 2, and 1. And when things in row 3 are built in terms of things in row 2 and 1, and things in row 2 are built in terms of things in row 1. And this is what we mean by levelization. And so if we pick something like F, we can get the in-place references. We say we're going to use F. We get all of these without moving them anywhere. This is by reference. And we have a subsystem prefabricated, done, and we can use it. This is how we find things because we have a curated collection of prefabricated software. So what we're doing is we started out in 2020 with a certain faster, better, cheaper design space. And then over time, we moved it out because we developed more and more prefabricated components. But the funny thing is that we not only moved it out, but we moved it off the axes because because there are prefabricated components, we can't make it slower, worse, or more expensive than a certain amount because all of those things are built into our software capital infrastructure. So if we were stubborn and did it the old way, like if back in 2000 when I joined Bloomberg, we kept doing the same old, the productivity would have increased, but then it would have reduced due to increasing costs of ownership and replication and whatever. But by joining Bloomberg and by changing the way we do business, we created software capital. And you'll notice that for a while, yes, the productivity was lower, but there came a point at time T2. At T1, the software capital took off. At T2, the productivity reached where it would have been before, and then we never looked back. And this happened just a few years after we started, and it's been about 15 years now since we've been in full fury, and no one would ever say to do otherwise. So I want to emphasize that when I started writing this book and when I drew this picture, this was a theory. We're now publishing the book 20 years hence and saying it's not a theory, it's a fact. So you start off with an application and you have a bunch of things and software, and there's nothing to depend on, so you're just stuck. Then the software capital team comes along and extracts the good stuff. And this is a special team skilled at doing this because application developers are typically not initially inclined to do this. It occurs over time, but it's not something that starts out. So when you're starting out, you need people who are focused on this. Then that application team can then retool themselves in version 2 to take advantage of these higher quality components, and then they have less maintenance version. Application 2 comes along, they can start right away using these components. More code is extracted, and then in version 2, they can take advantage, and they no longer have to maintain as much. And of course, application 3 benefits from all the previous work and so on. And by the time you get to the 5th and 6th and 7th application, it's just like when you started work at that new company. You're now in the groove, you've built up all of your infrastructure, and you're cruising, and your productivity is much, much higher, and your productivity continues to grow. Now, to answer the specific question, you have something here, you have some software infrastructure, and it turns out the component U requires an incompatible change. What are you going to do? Do you copy everything over and change it? And of course, the answer is no. The way you do this moving forward is you very surgically change U to a U prime side by side. So you still have U, and U is still stable, but you also have U prime. You then build up everything else along the side, and now anybody coming along can use either X or X prime, W or W prime, V or V prime, U or U prime, because they're still there. Nothing's changed. You have a stable infrastructure, and you have two solutions instead of one. Now, there are times when that's not possible, when the type of the entity itself is a vocabulary type. A vocabulary type is something that's used widely throughout the interface. In those cases, you do have to preserve type, and that is an advanced topic discussed in the book. But when you're not dealing with named types that are widely used in the interface, like a date or a time or a string, then this is exactly what you want to do. And of course, anytime you're dealing with functions, this is exactly what you want to do. So here's an application. And the application is itself a hierarchically reusable system embedded in a hierarchically reusable system. And over time, over 20 years, let's say, we'll grow something where all of the software that we've written lives in this hierarchical repository of reusable software. This is the goal. It has to be done mindfully. If we don't, it'll look like this. So as the final slide, the original purpose of this was to reduce the cost due to repetition of writing the same software over and over and over again. That's how I sold it to management initially. But the real advantage is that when the next application comes along, most of the work is already done, and the cost can be amortized over many versions of many applications. And that is the end of my talk, and I will take questions for the next few minutes.
Yeah, we still have some time for the questions before we move to Zoom room where we can answer more. Actually, there was a question from our chat, like, what's your opinion on the book called Clean Architecture, A Craftsman's Guide to Software Structure and Design? It's like Martin Sirius, if you know that.
Yes, I know Martin. I have to confess, I've had that book and I've glanced through it. I cited many of Robert Martin's books. In fact, he's the first person to talk about the notion of dependency inversion, and he's the only one to even hint about physical design before my first book, Large Scale C++ Software Design, came out in 1996. So I'm very familiar with his work. I have not read through his book. I have discussed it with people who have said that many of the ideas in that book are consistent with mine. And so I will have to simply say that, unfortunately, I can't comment to the detailed extent, except that we share a lot of common ideas regarding physical software design, and dependency inversion is one of them.
Okay, thank you. Talking about the software capital, I actually remember the talk by David Sankel at CPPCon, I guess, about building software capital. And there were a few words from David, which I would like you to comment from this talk. So one was that David, at this talk, he stated that tooling is actually super important for building the software capital. And he listed the tools like the checkers, like the Clang Tidy, or like Clang format, or the unit testing tooling. So do you also think that the tooling is important for successfully building the software capital, or you're like not that tooling person and more for more general concepts here?
Well, here's the thing. I believe in tooling that is customized to a process and not vice versa. So when the tooling serves the software design process that I'm trying to put forth, then absolutely. So for example, if you have a design and you can extract the physical dependencies from the design quickly and then display them, that's awesome. And in my 1996 book, I provided a program to do that. So those kinds of things are extremely important. Being able to make sure that design rules aren't violated using static analysis tools. We have written our own static analysis tool. It's called BD Verify. And what it does is it actually is the static analysis tool paired with the book that does all the kinds of analysis that we're talking about. So is tooling important? Absolutely, because without it, you're relying on human beings to make uh, uh, to make checks that computers can do far better. So anything that a computer can do, it should. On the other hand, take for example testing. It is a common misconception that testing frameworks will help you test. It's not that they won't help you test, but if you don't know how to test, they won't help you. So the testing itself is hard. It's impossible unless you design things to be tested. And then once you've designed them to be tested, you have to know how to test them. And once you know how to test them, you don't need a framework. But if you want to use a framework, it can be helpful. Does that make sense?
Yeah, obviously. Okay, so
But I
we
want to
just have
reemphasize the testing. The testing
minutes.
specifically is the hardest. Okay, go ahead. Go ahead.
Yeah, just finish your word. That's fine.
I was just going to say that in particular, the hardest thing about testing is testing. And the framework is the least of your worries. That's all I wanted to say.
Yeah. Okay. So maybe just very quickly before we move to Zoom, you can answer just one question. What's the period in which this library-based design, this partitions design, actually pays for itself?
Okay, that's an interesting question. Obviously, this is very subjective. It's a matter of scale. If you're doing something the size of Bloomberg, I would say that it took about a year for me and a very small team to lay the foundation before there was sort of like the spark. I would say it was, but again, remember this is 20 years ago without an SDL and having to rewrite. There's a lot of stuff going on there. So if it had to be done over again, it would be much faster. We know a lot more now. But in history, it was probably from 2001 to 2004.
Okay.
I would say
Okay.
about
Thank you.
by
Thank you.
between that time frame, but after that it was good. Yeah.
Okay, so I suggest everyone just move over to Zoom now to continue the question session. So we still have some questions to handle together with John. And thank you for the presentation.
No, you're very welcome. Thank you for having me.
John, thank you. It was exciting topic. Anastasia, thank you for your expert opinion. And now you can move to discussion zone and continue.
Thank you.